Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is dedicated to the beginning of inverse trigonometric functions, really defining them, learning about them, kind of an initial opening sequence for the inverse trigonometric functions. It doesn't matter what textbook you're using, this topic is the same in all textbooks. So it doesn't matter if you're in a trigonometry course or a pre-calculus course. I would probably treat this material the same exact way in both of those courses because it's such an important topic for calculus that I end up going into detail in both of those courses. So if you're in a pre-calculus course and you're watching through my pre-calculus videos and all of a sudden this comes up, it's because I would normally cover this with this much detail in a pre-calculus class as well. Same thing in trig. So let's dive right into it. We already know that if we have a one-to-one function, and one-to-one function just means that that function has an inverse, then if our function's y equals f of x, well, that implies f inverse of y would equal x if we can find f inverse. Remember, there's some characteristics about one-to-one functions that are going to be critically important. The main characteristic is that a function is one-to-one if it passes both the vertical line test, that would create it, or that would label it as a function, but it also has to pass the horizontal line test, which in this case, this graph right here does not. So this would not be one-to-one. We need our functions to pass the horizontal line test in order to be one-to-one functions and therefore be invertible. So which of the trigonometric functions are actually one-to-one? At this point, you should have already gone through the graphs of all the trig functions. So let's go ahead and review them to see which ones are actually one-to-one. Well, let's consider first the sine curve. There's the sine curve right there from 0 to 2 pi. It goes on forever in both directions, and it's periodic, 2 pi periodic there. And you can easily see this does not pass the horizontal line test, so it's not one-to-one. Likewise, since the cosine really is pretty much like the sine, and it just starts high, goes low, and goes back high, but also is 2 pi periodic there, goes on forever, but it still does not pass the horizontal line test, so therefore the cosine is not one-to-one. Well, what else could be our hopes? Well, the cosecant latches on to the sine, both the maximums and minimums of the sine, and then you have these vertical asymptotes in here for the, oops, missed on that one, for the cosecant. But you can easily see the cosecant does not pass the horizontal line test, so therefore the cosecant is not one-to-one. Well, we have a similar issue for the secant, which is the reciprocal of the cosine. Again, it would latch on to the maximums and minimums of the cosine, and you can easily see it does not pass the horizontal line test, so therefore the secant is also not one-to-one. Well, our last bastions of hope are the tangent and cotangent functions. But unfortunately, if you take a look at the tangent function, it has a bunch of vertical asymptotes, and it repeats itself forever and ever and ever. And so therefore, it does not pass the horizontal line test. And the cotangent suffers from the same issue, right? The cotangent does this, and there's a vertical asymptote, and again, it does that, and there's a vertical asymptote, but you can easily see just from that graph, again, the cotangent does not pass the horizontal line test, so the cotangent itself is also not one-to-one. Therefore, it is not invertible. None of the trigonometric functions are naturally one-to-one. So I'm going to write that in here. Well, how in the world can we have a whole entire chapter out of every single, or I shouldn't say chapter, section, out of every single trig and pre-calculus book that's dedicated to inverse trigonometric functions, and yet none of our trig functions are actually naturally invertible? The reason why we can do it, or why we have these sections and why they're so important, is because we can force a function to be invertible by restricting its domain. So that's actually what we're going to do here. And I like to use Desmos to really showcase the choice for the domain restrictions. So I'm going to go ahead and hop over to Desmos here, and we'll discuss each function piece by piece and talk about wise decisions on how to restrict their domains. So what you see here is the sine curve. Let me actually color that to where it's a nice color, right? There we go. I like that color. And I'm going to also expand it a little bit. You can see right now it does not pass the horizontal line test, but if we start moving, maybe erasing part of it, we might be able to get it to pass the horizontal line test. Let me go ahead and erase some from the left and from the right. At this point, if we erased that much of it, it would still not pass the horizontal line test. Now, if I erased all of this to here, of course, that passes the horizontal line test. The problem is, what you want with an inverse function is for it to get all representative y values that you can. Now think about this function. What are all the y values that can pop out of the sine? What are all the outputs? Well, it goes all the way down to -1, and it goes all the way up to +1. So I need to get representatives from -1 all the way up to +1 as far as the outputs for my sine curve. So I don't want to erase this curve all the way to there, because I only get y values from a -0.858 all the way to a y value of roughly around 0. That's not good enough. So I need to somehow intelligently erase this. And so I'm going to do this. I'm going to erase all the way up to -pi/2 and erase here all the way up to pi/2. Whoops. Go back one. And you see that does actually pass the horizontal line test and the vertical line test technically. And so if we do that domain restriction right there, we have all the possible y values represented from -1 all the way up to +1, and it passes the horizontal line test. Now, we restricted the domain significantly to do this. I mean, originally, this function went on forever in both directions, and we erased an infinite amount of this function just to get down to this little subsection of it. But such is life. That's how inverses work sometimes. So for sine of theta to be 1:1, we restrict that angle theta to be in the interval from -pi/2 to +pi/2, including -pi/2 to +pi/2. Again, just to illustrate that on a graph here, that just means you get this part of the curve. It gives you all y values, again, from -1 to 1, which is exactly what you want. You want all your outputs, all your possible outputs represented. And so we get that. And it passes the horizontal and vertical line test, so it's a 1-to-1 function. So let's try the same thing with the cosine function. Here we are with the cosine curve. And again, we started erasing. Now, if I had gone from -pi/2 to pi/2 here, you would see it would not pass the horizontal line test. So that restriction, no good. So we have to reinvent the wheel here. Let's see what we can do. I'll start erasing from the left-hand side, and I'll get to this point right here to 0. And I'm going to erase from the right-hand side, and I'll get to this point right here at pi. Notice we get all the y values from a -1 all the way up to and including, whoops, it says undefined, but +1. And it will pass the horizontal line test. So as long as we restrict our angles, our domain for the function cosine to be between 0 and pi, it will be 1-to-1. Again, we just restrict the angle theta that we'd normally plug into the cosine to be between 0 and pi. The cosine curve from 0 to pi, again, looks like the following. We get all the outputs from an output of -1 all the way to the output of +1, and our function remains 1-to-1 because it passes the horizontal line test. Let's go ahead and do the tangent. That'll be the last one we do. Now here's the tangent. The tangent's kind of a funny function just because it has those vertical asymptotes in there. If I start erasing from the left-hand side, you'll see that no matter what, we kind of, we just have a lot of these lines in here, or a lot of these curves in here. This still will not pass the horizontal line test, but it kind of seems pretty natural that you might want just that middle section, right? So I'd like to remove everything up to pi over 2, or negative pi over 2, sorry, and everything down to positive pi over 2. So this interval right here from negative pi over 2 to positive pi over 2, that's the interval I'd like to consider so that my tangent is invertible, or in other words, that it is 1-to-1. Note that x cannot actually be a negative pi over 2 because that's a vertical asymptote, and the same thing about positive pi over 2. X can't be that because, again, that's a vertical asymptote. So very important that we not include those endpoints for theta, because we cannot plug negative pi over 2 or pi over 2 into the tangent anyway. And there's the summary right there. For tangent of theta to be 1-to-1, we restrict the angle theta, the argument of the tangent, to be between negative pi over 2 and positive pi over 2. Visually, we have this going on. So we have a vertical asymptote at negative pi over 2. We have a vertical asymptote at positive pi over 2. And yet, really what we're willing to accept is any angle between negative pi over 2 and positive pi over 2. Sort of missed that origin there. Sorry about that. But that would be, and I know that's not the prettiest function, sorry about that. But that would be the interval that we restrict to, and you can see that the function passes the horizontal line test on that interval. So everything seems pretty okay. Now, before we move forward, I just want to state that normally the sine, the cosine, and the tangent, don't talk about inverses, let's just talk about the sine, cosine, and tangent. They can take any angle. Well, maybe not the tangent, but tangent can't take an odd multiple of pi over 2. But both the sine and cosine, you can plug actually any angle into those functions. But once you see this inverse notation right here, and if it's attached to a trig function, then we have to consider these restrictions that I've written down here. So let's see the actual definition and then talk more about that. So the definition of inverse trigonometric functions: let theta be an angle. Then the inverse trigonometric functions are defined as follows. Theta equals sine inverse. It's how you would say that, just like you would say f inverse or something like that. Theta, which is equal sine inverse of y, means that y is equal to sine of theta. Now, I really want to drive this home. Before we continue, I really need you as a viewer, as a listener, to truthfully understand this. All the arguments, the inputs for the trig functions here, all of these are angles. All of these are angles. So you plug angles into trig functions. That's critically important that you understand that. You're always plugging in an angle. And right now, you've been working with trig functions long enough to say, well, of course I plug an angle in there. But trust me, you will get confused. So that's why I'm just making sure you note, we plug angles into trig functions. What we get out of trig functions, which I'll highlight in blue here, what we're getting out, and maybe I'll go ahead and use blue to point at these, are ratios. We get ratios out. Ratios, for example, a sine gives us y, opposite over adjacent. Cosine gives us, sine gives us opposite over hypotenuse. Excuse me. Cosine gives us adjacent over hypotenuse. Tangent gives us opposite over adjacent, that type of thing. They give us a ratio of two sides of a triangle. So all of these right here, this guy included, let me just put an arrow right there. All of these are ratios, those y values. The outputs for the trig functions are ratios. However, when you're talking about the inverse functions, the input for an inverse function is a ratio. You're plugging in ratios. So let me highlight all these, same colors. So I'm just going to make sure that we keep that nice, pretty relationship there. We plug in ratios into inverse trig functions, and their outputs, let me finish this. This looks like an absolute mess. I totally get it. And their outputs here, which deserve the yellow highlighter, are angles. So inverse trig functions, you plug ratios into them, you get out angles. And that's why I'm using theta. Often a textbook would not use theta here. It would use y's and x's. But I think it's so important for you to know inverse trigonometric functions always return angles. Regular trig functions, their arguments are angles. What you plug in is called an angle. Anyhow, so that being said, if we all can agree with that, these are just machines. I plug an angle into the sine machine. Out pops some ratio, maybe a half. If I want to know what a half leads back to as far as the sine is concerned, the sine inverse of that ratio, half, would return the relevant angle, pi over 6, for example. Okay, so that's just an important consideration. Anyhow, but that is not the only piece that can trip students up, because the sine and the cosine, their domains are all real numbers. We know that the tangent, it has some vertical asymptotes, so the tangent doesn't exist, or it's undefined, when your angle is an odd multiple of pi over 2. So each of these trig functions might have weird domain issues. That's fine. But the really hard part for students is when you get to the inverse trig functions and you find out that their outputs are restricted. So for example, if I told you I have the sine inverse of y equals an angle, you should be okay with that. Sine inverse turns into an angle. Got it. And that means that y is equal to sine of the angle. But there's one simple restriction. The angle can only be between negative pi over 2 and positive pi over 2. And that's because of that restriction that we had to force the sine function to be 1-to-1 so we could talk about an inverse. So all of these conditions right here on the right hand side of your screen are there so that we could talk about even having an inverse, because naturally none of the trig functions are invertible. So these are the domain restrictions to make them invertible. So again, sine inverse will return an angle where the angle is between negative pi over 2 and positive pi over 2. Cosine inverse will return an angle where the angle is between 0 and pi. Tangent inverse will return an angle. I should zoom in like this. Tangent inverse will return an angle, and the angle will meet the conditions that it must be between negative pi over 2 and positive pi over 2. And it won't include negative pi over 2, nor will it include positive pi over 2, because tangent isn't even defined there. Now, the other three are here for pre-calculus students. Normally, in a trig class, you would not deal with the cosecant inverse, the secant inverse, or the cotangent inverse. Those are a little more challenging, but they're necessary. At least technically, at least the secant inverse is necessary in calculus. I mean, a big necessity in calculus, in fact. So if you are in pre-calculus, the angle that the cosecant inverse is going to return is going to be restricted to be between 0 and pi over 2. But unfortunately, that won't capture all the outputs that the cosecant has. That only captures the positive outputs, and cosecant can be negative. So we also include pi to 3 pi over 2. Notice those are not connected. They're not what I would consider to be connected quadrants. In fact, now that I'm saying that word, quadrants, let me back up a little bit, just a teeny little bit. If you think about quadrants and trig functions, all trig functions are positive in quadrant 1. And notice, as far as angles are concerned, the sine inverse returns angles between 0 and pi over 2, right? I mean, it technically returns more than just 0 to pi over 2. It returns negative pi over 2 to pi over 2, but it includes angles between 0 and pi over 2. Cosine inverse. It'll return angles that include those between 0 and pi over 2. Tangent inverse. That includes angles between 0 and pi over 2. Cosecant inverse. That includes angles between 0 and pi over 2. Secant inverse. That includes angles between 0 and pi. I feel like Oprah Winfrey here. You get an angle between 0 and pi over 2. You get an angle between 0 and pi over 2. Yeah, anyway. And then cotangent inverse also returns angles that are included between 0 and pi over 2. The reason why is because when you find the inverse of a function, you want to make sure as many of its outputs are represented. And we need all the positive outputs for each of our trig functions represented. Luckily, all of our trig functions are positive in quadrant 1. So anytime that you have a inverse trig function that's related to a positive ratio, the angle that's going to return is a quadrant 1 angle. Actually, that's so important. Let me write that down. Anytime an inverse trig function is evaluated at a positive ratio, remember inverse trig functions, what you plug into them are ratios here. Well, that was supposed to be a highlighter. It wasn't. Anyway, anytime that you plug in a positive ratio, the inverse trig function returns an angle, which it always does, but it will return an angle between 0 and pi over 2. It might not be at 0, it might not be at pi over 2, because some of the inverse trig functions can't return at 0 nor pi over 2, but they can return between those. So that is one huge deal. Now, think about the sine. The sine function, it's positive in quadrant 1, because everything is, and it's also positive in quadrant 2. The tangent is positive in quadrant 3, and the cosine is positive in quadrant 4. So it would not make sense for the sine inverse to return angles in quadrant 1 and quadrant 2, because all the positive ratios have already been represented by angles in quadrant 1. I don't need I don't need ratios represented or positive ratios represented by a quadrant where sine is positive anymore. I already have that. That's quadrant 1. I need a quadrant where sine is negative, and that'd be this quadrant right here, 4. And notice, if you think about angles, that's negative pi over 2 to positive pi over 2, and that's exactly what the inverse sine returns in. Negative pi over 2 to positive pi over 2. Now think about the cosine. The cosine is positive in quadrants 1, like everybody else's, and quadrants 4. So saying, oh, I want my cosine inverse to return angles between negative pi over 2 and positive pi over 2 would be bad, because you would only get positive values of a cosine. So we restrict the angles for the cosine inverse to be from 0 to pi, because in quadrant 1, the cosine's positive. In quadrant 2, we get the negative values for the cosine. That's why we made that distinction. The tan inverse is kind of the oddball. The tangent inverse, you could have technically used quadrants 1 and 2 for the tangent inverse, because tangent's positive in quadrant 1 and negative in quadrant 2. But by convention, we use quadrants 4 and 1. And it's mainly, I think, I'm not sure about this, but I'm almost positive this is why. It's because the tangent's continuous between those two quadrants. If you go between an angle of negative pi over 2, we'll just do it like this, to positive pi over 2, the tangent's continuous. But if I had gone from quadrant 1 to 2, in other words, from 0 to pi, then we would have, first of all, this. You'd have this red function from 0 to pi. And it's just got that break in the middle of it. And that's kind of worthless. We don't want that. So it's much nicer to just restrict it to be only from negative pi over 2 to pi over 2. And it has that nice smooth connection. So that's what a trig student would need to know. And a pre-calculus student would need to know the bottom 3 in addition to the top 3. In the bottom 3, the cosecant inverse of a ratio pops out an angle. Okay, I'm fine with that. And remember, the cosecant is the reciprocal of the sine. And so we want 2 quadrants, one where the cosecant is negative and one where the cosecant is positive. Well, we know it's positive in quadrant 1, so we're going to include that. And we could have included quadrant 4 because that's where cosecant would also be negative. And that would match beautifully with the sine inverse, which returns angles between negative pi over 2 and positive pi over 2. But the reason why we don't is because of something very important in calculus. Instead of quadrants 1 and 4, we choose quadrants 1 and 3 for the cosecant. Quadrant 1 for the positive values of the cosecant, and quadrant 3 for the negative values of the cosecant. Same thing for the secant inverse. Secant inverse will return an angle. And that angle will either be in quadrant 1 or quadrant 3 again. And yes, we could have chosen quadrants 1 and 2 for the secant inverse, but we didn't because of something from calculus that's necessary. So we stick with quadrants 1 and 3. And finally, the one I've never honestly used, the cotangent inverse. And so that should tell you how important a cotangent inverse is. It returns an angle, fine. And the angle it returns is between 0 and pi, or in other words, it returns an angle in quadrants 1 or 2. Now, why quadrants 1 or 2? Because the tangent is positive in quadrant 1, cotangent's positive in quadrant 1, just like every other function. And you had your choice, either quadrant 4 or quadrant 2, and for some reason they chose quadrant 2. And I think it's mainly because the cotangent's continuous between angles of 0 and angle pi. So again, that's probably convention, but it's true. That's a lot to digest. I mean, really, I totally get it. Usually a trig student looks at this and they're very intimidated. It's actually not that bad. You get used to it, but it is an immense weakness that students have when they reach calculus. So I want to make sure that you know how important these are. I want to drive home the fact that yes, you plug angles into trig functions and you get out ratios, but that's not what you do with inverse trig functions. Inverse trig functions, you plug in ratios, you get out angles, and those angles are going to be restricted. Let's see, what else do we have here? I made this little note down here because I use the inverse notation quite frequently with that -1 that looks like an exponent. It's terrible notation, honestly. But there is a standardized notation for the inverse trig functions. It's arc sine of y, arc cos of y, and arc tan of y all mean the same as sine inverse of y, cos inverse of y, and tan inverse. So if I happen to have an example that uses the arc notation, you should now know it just means the inverse notation. It just means the same thing. Now I have this page here just as a summary, and it's a theorem, but still kind of summarizes what we just said a few moments ago, the domain and range of the inverse trigonometric functions. So again, just remember, input for these arc functions. Notice I used the arc notation here just because I wanted you to get used to both. The inputs for the arc functions or the inverse functions are ratios. The outputs are angles. Theta is just an angle. Okay. And the domain, which are the inputs, which will be the ratios, the domain for the arc sine, what you could plug in, are numbers between -1 and 1. And that's because the sine, its outputs, go between -1 and 1. The inputs for the inverse cosine go between -1 and 1. And that's because the cosine has outputs between -1 and 1. The inverse of the tangent, the inputs for it, go between -infinity and +infinity. And again, it's because the tangent's outputs go from -infinity to +infinity. And you could see the same things justified down below for the arc cosecant, the arc secant, and the arc cotangent. Notice the domains here, all these domains are actually the ranges of the original trig functions, So they're the outputs of the original trig functions. Again, -1 to 1 inclusive, those are the outputs of the sine function. Anyhow, now let's talk about those outputs of the inverse functions. We just talked about the domain, the inputs. Let's talk about the outputs. Those are the restrictions, are the outputs. So those are the important conversation. Again, the range for the arc sine is going to be a set of angles between -π/2 and π/2, quadrants 4 and 1. The set of outputs for the arc cosine are angles between 0 and pi, again, quadrants 1 and 2. The set of outputs for the arc tangent is a set of angles between -π/2 and +π/2, not including those edges because the tangent's not defined at those edges. And you can see the set of outputs for the arc cosecant, arc secant, arc cotangent. They all return angles. And again, they will all return angles in quadrant 1 and then a different quadrant where those functions are going to be negative, specifically quadrant 3 for the arc cosecant and arc secant, and quadrant 2 for the arc cotangent. Now that is a heavy amount of material to digest. I really recommend writing this information down, printing it out, taking a screenshot, whatever you got to do, because this stuff right here is critical. I mean, it's just like you have to know how to add when you get into trig and into calculus and all those other courses. That's how important trigonometry is. It has to be there like you've been doing it your life. So anyhow, all right, so that will finish just our introduction in this video. The next video will start evaluating inverse trig functions.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.